Okay. Good morning, everyone. Let's start with the Prarthana. Om Ganana Tva Ganapatihim Havamahe Kavim Kavinamupavashravastaman Jyeshtarajam Brahmanam Brahmanaspata Anashranvannotibhisi Dasadanam Gurur Brahma Gurur Vishnu Gurur Devo Maheshwarah Gurur Sakshat Parabrahma Tasmai Shri Gurave Namaha Saraswati Namastubhyam Varade Kamarupini Vidyarambham Karishyami Siddhir Bhavatu Me Sada. So hello everyone. Sorry for the delay. My Zoom went through an update and I had to actually reboot it. So we'll get started. Today, what we want to do is to cover some of the background in AI and very specifically the topics that are kind of pertinent, like basically the inflection points in the whole history of AI and where all it kind of made some huge progress, and what are all the, and most of these inflection points we will touch in subsequent topic discussions on when we draw parallels between what we see in our literature to the techniques that are used in there, right? So let's do that, and we will start with, okay, what is the perception of AI today before we even go into what is AI, right? So my advent into AI was somewhere like 10 years back when we wanted to use AI for cybersecurity. And during the time, pretty much it was more called machine learning systems at the time. And the kind of it was a bit of a laborious process in a sense. You have to figure out what kind of data you want, depending on what is that you can is available for you at runtime to be able to predict things, and then you have to go through a lot of process to make sure that you can make the results predictable and deploy them, right? And given that we were using it for cybersecurity, to some extent, when the model said, oh, okay, you know what, this is compromised or this is not compromised, then you also have to substantiate on why it is predicting, right? And to some extent, the cartoon on the left kind of maps how we were actually dealing with the problem. So what you may have to do is, like, when you didn't get the results that you expected it to see, you will have to painfully go through, sift all the data to really figure out what are all the exceptions that you have seen, the outliers that you have seen that is probably screwing things up, and then spot them and to make sure that they are labeled really properly. And I mean, some of the terminologies that I'm using we will cover, but so that is kind of how the whole process was. It was pretty laborious and pretty much, and I have used this cartoon many a times, where sometimes if it doesn't make sense, you have to just go back and really retrain with appropriate modifications on what you think is what is causing the problem, then come back. If that doesn't work, try something else, and things like that. So that is how where we were. And today, if you look at it, I was just watching a lot of now in YouTube and other places in social media, you can actually see people are more scared about, okay, AI taking jobs and whatnot. And pretty much it is, people are like so scared about the advent of AI right now. And pretty much the cartoon on the right is what epitomizes the state of AI today, right? And people are a bit worried about it, but the thing is, like, they can't do anything about. So we'll say, okay, maybe I can retrain me on. Okay, maybe I can learn to use ChatGPT or and in whatever way I think it would suit me, and see whether I can go along with it, right? So that is kind of where we are right now, and it's a double-edged sword. To some extent, there are one end of the spectrum, or kind of people who are like, oh, it's like the somebody who has a hammer, pretty much every problem looks like a nail, kind of that stuff. Okay, we can use it everywhere we want without looking into what is the use case, why is it even appropriate to use AI and all that stuff, right? So that's kind of where that is one of the end of the spectrum. The other set of is like all about doomsday scenarios. To some extent, their worry is also validated, because one of the huge problems these days is essentially fakes, right? Fake videos, fake photos, or today you can even use it to generate uh, video at will, with whatever combinations that we can. And to some extent, some of the Gen AI providers are trying to put guardrails around what it can or it cannot answer, and what it can or it cannot generate. But still, it is not quite a foolproof, and we do end up seeing most of these. And then there is another set of people who have malicious intent, and they actually set up apps and websites where you can generate these um, malicious or contents that are vicious, right? I'm sure most of you guys have come across some of them, right? So, right. So let's moving on. Okay, what is happening? Okay, now what I think my animation is a little bit messed up there. Oops. It's taking time to render. Yeah. So if you look at the reasons for why it is the way it is, right? You can actually see that the left-hand side, what we have drawn as essentially the performance of A. So in this case, we are pretty much looking at this parameter called accuracy. So when an AI says that this is what it is, and how sure or how right is it when it actually says that? How does it compare to the reality, right? So let's say it says this is a cat. Is it really a cat, or it is thinking it's looking at a husky and thinking that it is actually a cat, or in something like that, right? So if you look at in the early 1998s to how the accuracy of the model has progressed, we have gotten to a point where it has improved a lot, and specifically since 2010, 2012, and we'll get into the details of why it is the way it is. And but the thing is, it has steadily improved on various kind of jobs. In fact, those colors indicate the um, different applications of where it is used. One of the things that it shows is actually handwriting recognition. There is a popular data set called MNIST. Without getting into these are basically nothing but handwritten digits that was used by the postal company to filter based on where these letters are intended to, based on the pin codes or zip codes, what the equivalent of pin codes used in the US today, right? And to detect those, and there were times when they had errors. And and if you look at that, that is kind of what is this 1998 model shows. That it's one of the very early lines towards the left that's kind of saturated all the way from 2002 all the way to up to 2010, and suddenly there was a jump. And that's exactly where is probably the inflection point of the current wave of um, the term that you might have heard called deep learning, or neural nets and things like that. So these are the terminologies that are used. So we learn to use those and use the graphics processing units that were once used only to render graphics for games. We learn to adapt it to do mathematical computations for training AI models, and that pretty much triggered the current wave of AI, right? And so when we measure the performance of AI, we use this term called human performance. It's like how well does the AI performs compared to how a human could uh, perform, right? For example, it's exactly, let's go back to you might have actually seen these captchas, right? Most of the websites, just to make sure that we are human, it'll ask us to write the digits or whatever that is displayed in a small text box, and it will compare against to make sure that it is us humans who are logging in, and it is not like bots which are logging into the system, right? So, and so basically it was considered that the humans are were better than AI, and we were using the human performance as essentially a comparative measure to figure out whether the AI, where does the AI stand, right? And with that inflection point in somewhere around 2010, it had started getting better so much to the point, for example, in some cases of, let's say, in terms of healthcare, we generally have a tendency, right? When a doctor says, you have something that you may have to do a surgery, or you may have to do like a little bit more risky procedure or something, we usually have a tendency to go and get second opinion, right? So that's kind of called a community performance. And the AI has surpassed not just individual performance, and it to the point it has actually surpassed even the even such community performance. In for example, in some cases where in healthcare where they use AI, it is compared again. There's a group of people who are essentially giving their opinions, and it is compared against what the AI model is going to predict. And only when it predicts, when its prediction is the same as the consensus of a group of doctors over there, only then it is actually considered the right prediction. And AI models have actually gotten better much. I mean, they have gotten much better than that. So in fact, you could see some of the lines go past this 100%. I mean, it is basically to say that they have surpassed human performance. There are cases where your image may be pretty hazy, that you might be double minds in figuring out what it is, or probably, let's say, the face is inverted and you are trying to figure out what this image is. The models have actually gotten better at figuring that out. I mean, for example, most of these language models today, they can handle today. I think I saw a news about where Gemini has been published with the support for 40 languages, including close to, I think, 8 or 9 Indian languages, where it can be used for various, not just translation, other things, for speech, text, and quite a bit of those. And it has gotten to a point where can actually do, it can handle 40 languages. And I know from a fact, because my son is interested in languages and he wants to be a polyglot, which is being able to read, write, and speak 5 languages, and that is essentially what he is targeting too. And some of these models can already do 40 languages with uh, with human or better than human performance at this point in time. And that naturally kind of gives us the scale, right? On one end. The other side is we are trying to deploy AI in more and more areas. Specifically, you might have seen in this Ukraine war, use of swarm drones, right? Where drones can actually act as a group and go and attack. And in this case, these drones they don't actually act as single entity. They can coordinate and communicate with them, and perform quite a bit of those uh, tactical jobs that previously would have to be deployed by humans. I mean, you might have actually seen some of these videos where uh, bots dancing to music and things like that from a company called Boston Robotics, now acquired by Google. You might have actually seen some videos going around in WhatsApp and stuff. I mean, how many of you guys have actually seen those videos? Have you guys seen them?
No, I have not seen. Hmm.
So there are some. I mean, just for the fun of it, I can actually send you some of those. I mean, they can really the moves that they do and the kind of acrobatic tricks that they do. I mean, on one end it's funny, and on the other end it actually is pretty. It's pretty amazing to see what they can do in a lighter sense. But if you just see at how they can actually be used to do other things, it probably gives you a slight scare on the other end, right? And it is important. And now, because of that, there are governments like for example, EU is very seriously looking into how do we regulate AI, right? At some point in time, when we had computers deployed in various fields, for example, hacking into a computer and other things were not considered that big of a deal. And over a period of time, when these attacks are like that could be something like denial of service, where you are not able to access a resource, in some cases hacking into the system and taking over and things like that, initially were not considered uh, as egregious or a crime. And at some point in time, the governments had to wake up. They had to formulate rules on what are all the red lines that they cannot cross. And that gave rise to something today called ethical hacking, where people, they they essentially work as if they are essentially trying to penetrate into a computer network. They do so using the vulnerabilities in these different machines, like your laptops, mobiles, and based on whatever operating system that you're running, they actually scan for those, figure out what are the vulnerabilities they can think, they think they have, and essentially use them to exploit those systems, right? In those scenarios, what they do is they do that and then go and inform those companies which essentially uh, publish these operating systems. For example, if, like let's say if they find a vulnerability in Windows, they go and inform Microsoft, and these companies now embrace this as a technique, and they do something called a bug bounty program. What it means is, if somebody finds uh, a major vulnerability, and if they end up informing them based on how dangerous and how bad it is, they actually give them they will reward them with monetary benefits and other compensations. Thereby, this ethical hacking is something that is encouraged, and people don't go into the black market and actually sell them for a higher price, which can come back to bite them, or used by state actors to essentially take over or threaten countries and things like that, right? So it basically gave rise to that, and that's kind of what we are I believe we will actually see happening in AI coming in the near future, where like even I think recently India passed a bill where if knowingly if somebody publishes misinformation, they will be essentially taken to task and brought under justice, right? Things like that. And what exactly are the definitions of breaking the law with reference to AI is what people are trying to fine tune and make sure that it can be abstracted enough and simplified so that it can be it can be understood and applied by the lawyers and judges to essentially serve justice, right? So that's kind of where we are at this point in time, right? So let's any questions thus far?
No.
Right. So now let's take a step back and just ask the question, okay, what is AI, right? I mean, we know it is artificial intelligence, but how do we define it, or what has been the generally understood definition of AI over a period of time, right? If you start looking at that, so first let's take a step back and see what is the difference between the traditional programming. Since with the advent of computers, the software programmers were essentially the most coveted job at that point in time, where people used to write programs, right? And that kind of has been taken over now. The AI models can actually write code and stuff like that, right? So what is the kind of difference between the original traditional programming and how are we actually making AI learn things, right? So if you look at it, the traditional program is something like this, right? Where you know what is the input data. Let's say in this case, you are using it for let's say for a banking system, right? So you know what is essentially the data in this case, right? So you are essentially doing some kind of a transaction, and there is a process on how you do that in today's when you go to the bank, how do you do it, and what essentially was done by the bankers behind the desk. And essentially you take that and you know what is that process, and you essentially write a program to generate that result. So let's say if the whole process was to transfer money from one person's account to another, so the process would have been to update the ledgers. So now these ledgers becomes soft ledgers like in databases and stuff, and then you write a program to essentially transfer the money in a very consistent way, right? So you have a defined data and you have a program, and essentially this program's job is to generate this intended result, right? And essentially the humans were writing the program to be able to cause the transformation of the data to the intended result, right? So let's say you are writing, let's say in this case, calculator is exactly that, right? So you essentially you say 1 plus 1, and you essentially add these two numbers and display the result. And in an event when things go wrong, or it is not the intended result, we call them bugs. You go back and you essentially take a look at the code to figure out, okay, what kind of a scenario was not taken into account. Now you essentially update the code to take care of that missing scenario, and essentially you publish a newer version, right? So that was what was traditional programming. So what is this machine learning or AI, right? So the machine learning and AI is, you have a good amount of data and you know what this result is. So let's say in this case, let's say there's a manufacturing company, right? And you have information about, let's say they are just making a bolt and a nut, right? And let's say they have information about, okay, what is the variance in the thickness that they can then that usually you usually see, what is the temperature at which they mold them, what is the how quickly they cool it down, to how long have they seen in the past, about how many percentage of bad bolts did this machine generate, and things like that, right? So you have a lot of this data, and you have, you know, how much percentage of error, or what is the amount of bad parts that they got, and things like that. So you have the result. What you do is you show enough, you give enough of the data, and you give the corresponding result. And then what you do is you essentially unleash an AI model. A model is basically nothing but it tries to basically predict this output. So you given a set of parameters, it will tell you whether this process will produce how much percentage of bad bolts. Let's say in this case it is 0.1%. And then they look at one of the old batches about what it did, and they figure out, oh, no. In this case, it does only give you 0.05% of the bolts were actually bad and not actually 1%. And then they go back to really figuring out, okay, in this case, the temperature variation during this whole process was, let's say, like 0.5 degrees centigrade. And that's exactly why it resulted in a higher rate of this, right? So what you do is, so you essentially give the model on how to measure this error. And then you basically tell this model saying, no, you know what, you have to pay attention to this temperature a little bit more. And now the model learns this and essentially tries to predict that. So the way that is done is basically using mathematical functions, very simple things. Let's say you are trying to add 1 plus 2, right? Let's take a practical example. So the models are initialized with this addition operation being something where it says initially it comes back and says 1 plus 2 is, let's say, 23. Now you have an error function. So you know the answer is 3, and you know it produced 20. So now you tell the model that, oh, you know what, you are 20 more than the intended value. And how do you do that? You basically subtract this and say, find the difference, and say, oh, this is 20 more. In some cases, it can come back and say, oh, 1 plus 2 is 1, right? And then you say, oh, no, you are 2 less than this. So you have a way to measure this error and have a way to feed it back into the network, into the model, to correct for itself. And you do this for enough examples. You just don't take like 1 plus 2 and you make it predict 3. And then unfortunately, if you don't have enough examples, it'll even say, oh, 2 plus 4 is also 3, right? So instead, what you do is you take enough amount of data and you have the intended result. And then you essentially provide an error function on a case by cases. case basis, and then you measure the loss, which is essentially measurement of error across all the samples, and provide a way for this model to autocorrect itself. So, for example, how many of you guys have read, done a subject called something like numerical methods in either your early in your school or in your engineering or in one of your
Yes, I have
sorry.
done it. I have done it.
Right? So this is exactly like that. So what you do in numerical methods is first, so for example, I showed you the series for pi, right? Which is 1 minus 1 over half plus 1 over 3 plus 1 over 5. It should basically give you pi over 4, right? Pi over 4 will be what? So let's say 3.12. If you have, let's say if you assume it to be around 3.2, so the value should converge around 0.8, right? When you start with the first term, it has a value of 1, which is definitely more, right? And then you add up, you subtract half. That gives you 0.5, now which is actually less than the intended value. Then you add plus 3, right? So you add enough terms, and it essentially oscillates around the intended value, and it goes up and down and up and down, and finally converges at the right value. That is how what we used to do called numerical methods, right? This is almost exactly that, where what we do in this case is you give a way to measure the error, and you give a feedback. So let's say the first time it says 1 plus 2 is 23, you make a correction, the next time it actually predicts, let's say 1 plus 2 is 70. I said, no, it is better, but not right. And then next iteration, it comes back closer and predicts something like 1 plus 2 is 7, right? And now it says, no, it is still wrong, but the margin of error is much lesser. So at some point in time, it converges to saying 1 plus 2 is 3, but whereas somewhere else, it might end up giving you some wrong results in other sin, right? And what you do is you make sure that you correct this error for all the scenarios, and finally it comes back and produces a model that can essentially do addition, right? The reason for, instead of writing a program and doing this, right? For example, let's take an example of, you guys all have use emails, and you know about spams, right? What in that email gives away saying that it is actually a spam? It's a very uh, very subjective opinion, right, in some sense. So you look at a few things, or it might have some dubious offer, the email might come from something really that you might have not received an email from before, or the offer might be too good to kind of it might be too good to believe, and things like that. So now what you do is, how do you actually quantify that? That's kind of what it is, right? So in this case, so that is kind of what that whole training process is. You give enough good emails, you give enough spam emails, and you say this is the data, and this is a spam email, or this is a good email. So a valid email. So, and you essentially give enough data, and the model learns to actually predict it. So what it finally throws out is the model, which is the equivalent of the program today, right? So for this, early days, we used to do something called what used to be called machine learning. Is the data used to be, let's say, in thousands or maybe like tens of thousands of samples. But today's model, where we use deep learning methods or neural networks, as they are called, the sample data runs into billions, or maybe even like tens of terabytes of data that that these models train on. So, and that is exactly why, well, that is one of the reasons why the models actually perform so well, because they have seen so many samples and so many variations, and they know in abstract sense how to essentially go about that problem, right? So that is essentially where these models get better over a period of time. Okay, and that's kind of what you call it as machine learning / AI. Right? So you guys got the difference between these two? I know some of you guys are from IT background, but I'm just kind of making sure that everybody gets on the same page. So far, so good?
Yeah. Yeah.
Okay.
At least for me.
Huh?
At least for me, I don't know about others.
Yes, yes, for us all.
Okay, So now there was after like maybe in the right round about like 2015, 2014, maybe sometime around that time, there was another methodology of how you could train these models, which you might have seen a kind of news where initial news where uh, I mean, like chess, all the chess champions playing against a computer, winning and stuff like that, right? Where these computers were trained to play chess, and they would play against the grandmasters. And there was a point in time, the first time when it actually beat the grandmaster, it was big news, right? Such models are trained in a slightly different way, where what you do is, so the act of playing chess and the rules are very well defined, right? That essentially defines the environment. And what you do is you make the model predict an action. Okay, play the pawn or play the rook or play the bishop, and when you can play, when you cannot play, or is it safe to play such a move and all that stuff, right? So all that are basically actions. You have various options, and you let the system uh, propose an action. And for that proposed action, based on the known rules, what you do is you you essentially produce the next state, which is if it is a valid move, and also then you associate a reward with it. Let's say when you are able to take a pieces of the opponent, then it has a higher reward. But that doesn't mean that you just go ahead and take the opponent's pieces and in the process give away yours as well, right? Your final goal is to essentially checkmate the other person. So there are going to be long term rewards, there is going to be short term rewards, right? And what you do is you essentially, these rewards systems are essentially defined around the environment. So basically, the agent to propose actions to the environment that will essentially result in a checkmate of the opponent. So what you do is, so you have an environment which can essentially produce the next state and also tell you what is the reward for that such an action to the agent. And the agent essentially goes through all the sequence of moves that it did and learns what is the right way to play chess and how to actually win over an opponent who as good as a grandmaster, right? So this is essentially one of the techniques where it is actually used in robotics. For example, these robo arms and other stuff, that the video that I talked about where these things dance and all that stuff, right? So those actually use these techniques. This is used to be called reinforcement learning, and now the reinforcement learning is also going through quite a bit of changes, like in other areas, that there are techniques like MPC. There is even in the learning process, it was started with something called Q learning, and then there was like teacher student learning. There is an learn by example and quite a bit of stuff, right? So it is today when you say that you are actually working on AI, it's actually saying something like, okay, I'm an engineer, which doesn't say much, right? You need to actually say what even, what field of engineering you are and what kind of work that you are certified to do, right? Even if you say you are a computer engineer, or it just doesn't really kind of cut it today, right? So there are computer engineers working in banking industry, like on the database systems, embedded systems, AI engineers, people who work on building ASICs and whatnot, right? So it's as now AI is a field that has become almost like that. So there are people who work on cognitive recognition problems, people working on language, and people working on RLs, basically these reinforcement learning kind of things. And now, for example, ChatGPT is essentially uh, it's a kind of a two-layer system where there is a layer that understands the whole English on what it is responding and all that, and think of it like another layer outside that tells how to respond back and what is actually a human-like response. And that essentially takes a piece from the right-hand side, which is essentially reinforcement learning, right? So it now there are models have are so sophisticated that it takes a piece from different techniques and they are all put together, and which is one of the reasons some of these models have parameters in some sense. For example, the addition, we said, okay, you take two parameters and you have a lot, how many intermediate states it produces before it produces the final result, right? So these intermediate results are essentially stored in some numbers, set of numbers. And how many set of those numbers defines how complex a model is or how large the model is. In today's scenario, I mean, previously, when you used to, when the early models, the number of parameters could be measured in like maybe a few hundred thousands to millions. And now some of these models have like billions of parameters, and you can't even kind of host some of these models in a single machine, and you actually need multiple machines or multiple graphics processing units to actually be able to host these models. So they have become so big, and so the amount of knowledge that it so to say it can hold has actually has dramatically increased and improved. Okay, kind of guys get an idea about what is the difference between traditional programming versus machine learning versus the other reinforcement learning that I talked about. Good. Shall we move forward?
Yeah.
Okay. So now let's look at some of this different terminologies and a little bit of the history in there, right? So artificial and AI is not a new terminology. So it has been there since the 50s, 60s, and 70s, where you might have heard of these languages like Prolog, Lisp, and things like that. They were what do we used to call them? So for example, Prolog. So these used to use this technique called very close to what in today's terminology called decision trees. So you ask a question, you get the response, and you essentially follow one or the other path of reasoning, and you finally arrive at an answer, right? So that kind of what was uh, um, that the sequence of reasoning that usually humans end up doing used to be called as artificial intelligence, right? Expert systems. That's exactly what it used to be called, right? And it used to be in kind of doing early diagnosis of diseases and things like that. So they'll basically ask this sequence of questions. And in fact, even today, in some sense, the initial diagnosis uses a steps of process about what all symptoms that you're seeing to come up with some probable causes and things like that, right? So those were automated, and that was kind of what was called the artificial intelligence in those days. And then, and somewhere around late 1980s and 90s, I talked about this backward way of correcting using an error function, right? So, 1 plus 2 is 3, but if you propose 23, one simple function could be a difference between this, right? With a sign. So in this case, you have predicted plus 20 more than your original value. Let's say it came back and predicted 1, it says, okay, you predicted minus 2 compared to the original value. Thereby, it can actually go back through these different parameters and different layers. It can make corrections, and then again go through the same example and see what is the new predicted value is. If it has come down, then it is good to progress in that same direction. But let's say in this case, we made some correction, and instead of 23, it said 700 or something like that. Oh, what, you are going the wrong direction. Now we have to correct it in the opposite direction. Right? Previously, this used to, I mean, there were very many techniques that were tried out to do this kind of a correction in the model. At some point in time, during I think the late 90s, I believe, late 80s, I believe, there is this thing called gradient descent. So I might have to use. I'll probably come back to this and explain to you a little bit more. So there were a few important techniques that were proposed, and in the early 90s is when I told you about those handwritten digits. They were able to provide a model that with a reasonable amount of accuracy. If you go back to the previous slide that I had, where we showed um, the inflection points. If you look at it, 1998 around to 2000, you saw there was the probability of accuracy was somewhere around. I don't know whether you're able to see my pointer. Somewhere around 50% during 2001, right? And that went all the way up to very close to 92% in around 2012. right? So, and this initial jump up to 50, above 50 was provided because of that technique. When this gradient descent was essentially proposed, right? And then came the and then came the era of the 90s, where we were using the neural nets to be able to, and different methods were proposed. Uh, we will get into it a little bit about how these different model architectures were defined. There were various techniques, like, I mean, you might have heard of terms like support vector machines, gradient descent. Sorry, um, um, uh, um, I mean, let me not actually get in too much into the details of those names and stuff. So there were like multiple minor iterations of those that happened during the 90s that improved this model a little bit, right? So, I mean, they were broadly, I would say, called regression models. What regression means, that it is exactly like what different ways to propose to correct this error and be able to propose it, and how well you can adopt to proposing a method that can actually draw a line and you say above this is actually good, above this is bad, and then depending on the data provided, it can essentially calculate whether it is above or below and be able to predict that, right? And then came a little bit of these neural nets, which basically became a little bit nonlinear. Instead of drawing a line, you could basically draw a circle and say anything within that is good and anything outside is actually bad. And then you can use this model based on your data, where you can actually increase or decrease your radius of your circle to be able to do that. Okay, so that happened during that time. And in the early 2000s, there were some radical changes that came about, not quite in the area of machine learning, but in terms of the database systems. So we used to use primarily something called transactional database. You might have heard of this name called Oracle, and there used to be database administrator kind of jobs that used to be very popular during that time, during the 90s and some early 2000s. So what these are databases used in the banking transactions, where you want to make sure that you can provide consistent transaction. Let's say at the same time, two people are essentially trying to draw money from the same account, or two people are trying to deposit money into an account. So you want to make sure that these deposits go sequentially. And let's say there was $100, let's say 100 rupees in the account, and two people are trying to deposit 10 rupees. You want to make sure that one goes through when it becomes 110 rupees, and then the other one you want to send it through, making it 120. If both of them read, make the change and modify, it will eventually become only 110 when it should have been ideally 120, right? So databases, you initially had to make sure that the consistency had to be established. And there were databases that used to do that in scale, like which can take care of like thousands of transactions in a second and things like that. So that used to be what was the database systems. Then after that, we started wanted to use database for analytical purposes. When I mean analytical purpose, where you are saying, okay, you know what, or give me all the information about people who have account in this particular pin code. Let's say how many of people, what is the average value of the deposits on of people from this area compared to and some other area. So which we call today as business analytics, right? So we wanted to answer some questions based on the data that is already there, to be able to improve the business or improve the customer satisfaction, or help the customer manage their thing better and things like that. I'm just taking an example of banking because I'm assuming that you'll be able to relate to it more, and things like those, right? So you wanted to analyze the data and propose a little bit, propose things, and that needed a different kind of organizing that data. And there was a breaking um, um, methodology that came about during the early 2000s that gave rise to what we call as, let's say in some sense you can call them as big data, right? And the big data is now the databases can store gigabytes or maybe terabytes of data, and it can give analysis about be able to take these what we call as queries. Queries is essentially, you can say, like what the examples that I gave. How many in this particular which of these pin codes have accounts an average of, let's say, 20 lakhs, right? Obviously, we might be able to find some of these pin codes which have more affluent people in that area compared to uh, certain pin codes that may not have as many rich people in there, right? Things like that. So we want to analyze and these databases could process such queries and provide back information at scale, um, which the transactional database weren't good at. And that the second part of that analytical database was initially one of the major triggers for the current AI wave. I mean, people might actually think that it is during the 2010s. There was one groundbreaking paper that came about, which proposed using this graphics units that you was originally used to play only games to be repurposed to doing all these calculations to train this model faster. But the the methodology to handle huge amounts of data actually happened a bit earlier than that, and that probably was very instrumental in giving us the capacity to handle huge amounts of data in a much quicker way. Okay, so that's kind of how the original ones started about, right? And then and in 2010 is when the other second jump, the other graph that I showed you, right? 2010, there was a huge jump in the accuracy of this handwritten digits and uh, uh, figuring out these handwritten digits. I'll show you some of these examples in subsequent slides, where you will actually see sometimes people write 7 and correct them to be 2. They may write 1 and correct them to be 7. They may write a 0 and correct them to be 8, and things like that, right? And to be able to figure it out as well as a human can do, it needed quite a few techniques to be put in place to be able to get that level of accuracy. And that was essentially the wave that started during 2010. And then there were subsequent improvements, and we will see them one at a time going by to, and that essentially gave rise to all these different models. And there was another thing during 2015, which a model that was able to understand the semantics in the languages, where you can encode the meaning of words in a bunch of numbers and be able to compare whether the meanings are the same or the meanings are opposite. More like how you can represent a thesaurus in a mathematical form that allows you to compare and contrast the meanings and opposites. And that was one of the another groundbreaking approaches where our quality of translation started improving drastically. And then there were again there were different models and techniques that we'll talk about during the in the course of time, and which started improving uh, the quality of the models. And then we started looking into different types of data, like image recognition or cognitive recognition in a broader sense. Then language processing, natural language processing is another. And then then essentially these robotics kind of ones were separate. But then after that, we started merging these. You could actually do text to speech. You can actually do you can take from you can essentially do text summarization of images and things like that. So you give an image, the model will be able to describe what is happening in there and things like that. Right. So all those things started showing up, which resulting in today's uh, what we call it as generative AI, where you just give a few set of information and it can actually predict. You can, for example, the name ChatGPT might have come across many a times. You can just say, "Tell me a story in English." It'll essentially that involves a king, let's say a demon and all that stuff that sounds more Greek and things like that. It can essentially narrate you a story that's more Greek looking, which is closer to the Greek mythology and things like that, right? So we have come that far from all the way from just being able to ask a few questions to predict a diagnosis of a disease to being able to generate uh, more artistic content and things like that. Recently, there was a strike that went about in Hollywood where they wanted to limit the use of AI in generating creative content because they thought that their jobs were at risk, and using that might actually jeopardize the creative, or essentially it can come um as essentially an issue for the creativity that we actually see today. Right? So kind of get how the whole evolution has happened since then to now. And we will actually see when moving forward, what is that in this columnar database that was very critical, and what is that we actually see in actually Paninian system of grammar, which some of you might be already very familiar with. And we will compare and contrast, and I'll give you very simple examples to understand that and be able to comprehend the relevance of compare that with today. Okay, good. What is the time now? Do you want to continue, or we'll probably take a break and come back again next week? So we are almost in the last couple of slides, and with this we will be able to start up with the again going back to the Sanskrit side of it to be able to compare again some of these mathematical techniques and things like that.
Complete this.
Sorry?
Complete this.
Oh, you want to play this? Okay, we'll go through. So we'll talk about what is an AI. Today people think now most of us might think, oh, training the model is all that is happens in an AI, right? But that's not quite the case. So let's go back to this prediction of, let's say, bank give out loans, right? So if somebody comes by asking for a loan, there are many important things that goes behind in giving them the loan. Whether this person, how much loan this person has taken before and have repaid, what is the financial background of this person, does this person have steady income, where does this come from, one are there people who can essentially vouch for this person, saying that this person can actually pay back the loans and things like that, right? So the process of just giving a loan requires a lot of these parameters. And to let's say, and if we want to solve the problem of giving a prediction saying, oh, should I or should I not give a 10 lakhs of loan for this particular person, then we need to actually gather what are all the relevant data that can be used to predict this, right? I can't just say, oh, if the person comes at 9 o'clock in the morning, I can give the loan. If the person comes by at 2 o'clock in the afternoon, I cannot, right? That would be basically completely like nonsensical to make such decisions, right? So you have to capture what is the process today and take that data. And so and whether you can collect enough data at scale, right? Remember, going back to AI, is you need to have a lot of samples for these models to look at a pattern and be able to predict. For example, right, sometimes this finding of these patterns can actually be uh, kind of sometimes jaw-dropping for us. For example, one of the early models I heard in one of these conferences where when Google was trying to use the retinal scans for the onset of retinal, what do they call it? Uh, Retinal myopia or something like, basically degradation of vision due to diabetes, right? So they were using these retinal scans to predict the onset of these eye related issues, and they had taken enough data and they had trained and all that stuff. So after training these models, they went back to these doctors and they were reviewing the results to see, okay, whether this level of accuracy is acceptable for you guys to be able to help in your diagnosis and things like that, right? So this conversation apparently happened, and one of the engineer apparently asked, if I just give you the retinal scan, will you be able to predict the gender of the person? Right? And the doctors came by and saying, no way, that is not possible. It's like, I don't think you can predict whether the patient is a male or a female by just looking at the retinal scan. And this person came back and asked, why does my model has over 95% of accuracy in being able to predict it, right? And that is where the power of these models come in. So it can actually find patterns that are not humanly visible, humanly discernible patterns that are there in the data. So all we will might seen is like shades of red and white and what different shades of gray, right? And for a trained eye, at least they will, I mean, the doctors will be able to find, oh, you know what, you have excessive bleeding in the eye, or you have a higher pressure, or you are losing, you are losing essentially vision cells in this area, and things like that. But to be able to find a pattern to predict the gender may not actually be comprehensible by a human. But the models have seen some patterns to be able to predict the gender. And that is kind of where one of the initial like aha moments came about. So but the thing is, going back to this thing, so there is multiple steps in being able to go with predicting a model, right? First, you have to gather the data. Then what you do is something called data pre-processing. So let's say in some cases, you don't have a zip code. What is in, let's say, because people didn't collect it, or sometimes, let's say, they didn't get what is the current salary of the person to be able to tell whether that person can pay back a monthly premium of this much and things like that, right? And in those scenarios, you may have to fill in this data because you are not going to get a completely clean data be able to predict to be able to make the predictions. So let's say, I mean, there is a 10% of error in the data is actually nothing, and you need to be able to take care of those because there may be other fields that may have very important information for you to be able to make the predictions better. So which means you need to be able to clean up and process that data, right? We in the parlance of this big data, it is called extract, transform, and load. In what it means is you may have the data in a very textual form, which you may have to pick the right fields and essentially associate with your problem, the data that you're gathering for the current problem, and fill in those fields appropriately. And in some cases, you might actually have an account number that may need to be correlated to a person or a person's name, to an age, and to be able to get those relevant information to be able to make such calls, right? And things like that. So that is essentially called data pre-processing. And then what you do is you have to choose a model. What kind of a model will actually work for this kind of a problem? Then you train the model, and then there used to be multiple steps in testing the model. What you do is when you get, let's say, 100,000 samples, you don't use all that sample to be able to test it, or you to be able to train the data. What you do is you take 95,000 of them and you train the model and use the other 5,000 to check whether your model is actually predicting properly, right? And then what you do is you are, I mean, previously what we used to do is you actually used to have training data, then you test, and then what you do is you have validation. So whatever you use as test data can actually feed in and to fix your problems, but the validation set is essentially a pure data set that this model has to pass before you can actually let it out to do some predictions. And these days, we don't really need to, because the models have trained on so much of data that you can actually skip one of these steps and be able to use them in directly in for predictions. Okay, so that kind of explains so what it is. And there are multiple steps in being able to do that. And one of the important things in the final phase is, let's say, in this case, let's say there's a bank that is trying to use a specific model. One of the important questions they may have is, if it says, okay, reject the loan for this person, you might want to articulate it to the person who is applying for the loan and why they are rejecting that loan, right? In today's model, because it is multi-layered and most of it is mathematical functions, sometimes you may not exactly be able to explain the results of a model. It is essentially an ongoing field of research. The explainable AI or XAI is what is called, is one of important fields right now. We improved the accuracy so much, but we didn't focus enough on the explainability of the results as much, and which is one of the reasons why sometimes people get scared about using AI, or they don't have enough trust in the model to be able to do that. For example, self-driving cars, right? So humans may have a higher percentage of errors, but if the driverless car makes one mistake, it becomes headline news, right? But there are so many people dying in road accidents on a day by day basis, and most of them are actually due to human error, right? But if there is a driverless car that creates an accident, or even if it does something as simple as breaking some traffic rules, we actually see them, because we are kind of a little bit worried about whether it might cause bigger problems. So we scrutinize the performance of these models much more stringently compared to the humans, right? In that case, the only way to avert such concerns is to be able to explain the functions of a model on why it essentially says, oh, you know what, in this case, this person failed to repay a loan 3 years back, and that's why we are saying we cannot give them this person a loan. And if we can articulate that, then that actually uh, puts the banker at ease to be able to use a model to essentially to decide whether to give or deny a loan, right? So that is essentially one of the important uh, areas of improvement that's happening here. Otherwise, it essentially happens something like this, right? So yesterday and today, okay, yesterday you had 0 husbands, today you have one. It might, the model might end up predicting like, okay, so you 3 days, 3 months from now, you are probably going to get, so I don't want to explain the jokes. You can just take a look at it and to say you don't want to be doing those extrapolations. There is essentially a saying in the field of, it is like, correlation doesn't mean causation. What it means is, there is a proverb in my mother tongue Tamil that says, "Kuruvi okkara panamuzham விழுந்ததுன்னு." What it means is, right when the sparrow sat on the the palm tree, the palm fruit essentially fell down. It's just because it happened once doesn't mean that every time a sparrow sits in there, it's going to drop a drop of fruit from the tree, right? So that was correlation, and that's not essentially causation, right? So same kind of common sense applies to the AI models as well. So when a particular inference is due to causation and when it is due to correlation, we need to be able to emphatically be able to explain that, right? Otherwise, we'll get into some of these ridiculous uh, um, uh, extrapolations and stuff, right? So that's one of the things to actually kind of talk about. And as we go about in through this course, we will see the techniques that we have contributing to different phases of this AI workflow, starting from data gathering to data storage, and how we essentially explain the model, and how do we mm, how do we essentially protect, basically provide security to the model and things like that. So in some sense, we will see how we have various techniques in our literature that attributes to the various aspects of this whole ecosystem as in large, right? Make sense?
Yes.
Okay, so let's see. I think, I don't think we'll be able to finish it. I'm assuming this kind of is basically a logical point. There is a little bit more where I want to talk about that evolution and go into a little bit details on each one of them in a more with with a little bit more diagrams and graphics, where you can actually understand them visually than me generally talking about. Anything else, guys, compared to the last today? Was it too technical? I am actually looking for some feedback. Hi, go ahead. Is that Priya? Yeah.
Yeah. I want to ask with regards. No, today's session was good. It was very self-explanatory. Like you were very good enough to explain it to people like us who are not from that background. My question is regards to the example which you gave. With example of retina.
Mm-hmm.
I want to understand what was the data. Like in during that you mentioned that under layered. Like the normally what human can see or human can predict, that is not there. But beyond that, what kind of data were given to that understanding I want to have.
So
What data was collected?
so the data that was essentially given was essentially these retinal scans. I mean, just Google for retinal scans on images. You will essentially see like red arteries and essentially a circular blob, which shows the how, I mean, so when you go in to do these scans, you basically put your chin in some place and they basically take a, not an
No, no,
X-ray, but
that
a
I
pretty close
understand.
photograph of it, right?
What
And
I am
just that is,
asking is, my question is that when you said, when doctors see things, so we are able to understand. So that is, human can do it. But then you also mentioned in that there was underlayered information which was provided to this information which they collect so that they can derive the outcome.
yes, okay, okay. I can maybe go a little bit. So, for example, when a person says, okay, you know what, your vision is diminishing is because, so they may actually they may essentially point out a specific area in that scan. Let's take an example of an X-ray with a broken bone, right? It's much more easier to relate for everybody. So when the doctors can look at these X-rays, they can essentially look at, say, oh, you know what, there is a hairline fracture over here, or essentially there is a huge fracture here, or there is a complete dislocation and things like that, right? In when they say that, they essentially point out a specific area, right? An area of interest, and essentially also explicitly say, in this case, they may actually point out that white gap, and essentially say, okay, this is a complete broken bone. Compared to a dislocation, you will not see a broken bone, but you will essentially something that is coming out, that has come out of a socket and things like that, right? So usually there will be annotations in the diagram themselves or in the scans themselves that essentially points out where the thing is and what the issue is, right? And these are this information that is actually given to this model to train. And you'll say there may be various different types of defects that they can diagnose with an retinal scan. It may be as simple as, oh, you know what, you have bleeding in your retina, you may have, let's say, like swelling of these nerves. These are some things that I have kind of heard, I mean, overheard, given we have some doctors and some doctors in the family. So things like those, right? So you can essentially look at them and you make inferences based on specific information there in that image, right? And that information is what is actually passed on to be able to predict. And in addition, there is also other metadata like, oh, what is this patient's age, what is the patient's gender, maybe some additional information about what are all the past diagnoses or some conditions. Oh, this person had A1C levels are on this for this period of time, maybe history of A1C values or the recent glucose recording, or what is the degradation of the power in the eye over a period of time. So in addition to the scan, these additional information might also be given with what was the final uh, diagnosis for for the condition that they see in that scan, right? So now what you can do is you can use this information, some of this information as essentially cause and predict the effect. Like in this case, the effect was just what is essentially the diagnosis for this person. That was essentially the effect that we were trying to predict. But one of the engineers, they said, okay, given this all this information, can you predict the gender of the person? So he kind of took another use case and trained on that as well. And what he figured was able to, or he or she was able to figure out was that they were able to identify the gender with a very high level of accuracy. And that essentially is what was mind-boggling at the time. And now we know that there are like micro patterns that are not humanly discernible that these models can actually take a look at. For example, the driverless cars, they can probably identify the like the cars in the front based on even under heavy fog conditions or heavy snow conditions and things like that, right? Where humans may have trouble in essentially being able to visualize, right? So those are the things that those kind of the information that is given in to be able to predict. And it is up to the engineers to actually say, okay, in this case, can you predict the age, can you predict the gender? They can try a different use case and see what level of accuracy each one of these use cases are can be trained. And I said, oh, maybe I can't predict the age better, but probably I can predict the gender with a high level of accuracy, right? Probably this may be taken back to, I mean, using it in some forensic use cases and things like that. We may never know, right? things like that. Does that answer your question?
Not really, but these are the obvious things. But I wanted actually, like, say for example, when we are talking, these are obvious things. These are obvious observations which we obviously, when we're analyzing in normal day to day, also we analyze such things in our things. It's just not to just feed. So point is, when we are doing this, like when we are giving it to AI, or for example, the
Hmm?
information, processing this information. So also we give or do they have so many informations, the data which you have already said, there are multi data available to them. So in that
Hmm?
scenario, do they learn from these collective data, and they
Hmm?
analyze these in such a way that they understand that, okay, there is some difference sometimes which we human cannot analyze these, and
Hmm?
they try to find a little perfection about human intelligence or human understanding, and then they process this. So that underlying data, how they do, that is one of the thing. And the
Oh,
second
okay.
thing
Yes. Okay. Huh. Go ahead, go ahead, go ahead. So, I mean, I can answer the initial this question. So, I'm sure one of the you might have heard of something called ablation studies, right? Which is used in medicine about how, I mean, how do you essentially respond or analyze a function of a specific organ, or probably, let's say, in terms of drug discoveries and stuff. Okay, what component essentially allows these proteins to attach to specific molecules and things like that, right? So where the way you would do it is, you would essentially essentially mute a part of it, and and try to understand the functionality with and without things in place. For example, I mean, classic thing is during I mean the drug trials, right? In drug trials, what you do is you actually split the sample pool into two parts, which has, and who has and who doesn't. And into one set of people, you actually give the actual vaccine. The other person, you just give a panache, right? Which is probably just water or something, right? And then you figure out what you want to get as an inference there is only in the case of where you gave the vaccine, the people did not get the disease. In other cases, in the case where they just gave some panache, nothing. So the amount of people who got the disease it should be higher, right? That is kind of how you do it. Let's say in both the pool, the number of people who contracted the disease was exactly the same. Then you can conclude safely that this vaccine is of no use, right? And that is kind of how you do this testing. And the way you do that is making sure that you have two pools. One, you have the drug and the probability of contracting the disease in both cases, and essentially infer it from there, right? So similarly, the way we actually explain the models is you mute. I mean, the one of the techniques that we have today is essentially ablation studies. Even some of the later techniques that we will actually see is you will essentially mute some of these and say, okay, first, let's say this model predicts a cat, right? First, maybe I'll mask the eyes and say whether it continues to predict this as a cat. Let's say in this case, if it doesn't, so with eye it predicts properly, and without the eye it is not predicting properly, then I know that it is actually using some features in the eye to predict that this is a cat. You see what I'm saying?
yeah, I'm getting it out. Yeah.
So something very close to that is what we would do today, because we will talk about it. Different layers in these models the initial layer of the models will be able to detect like vertical lines versus uh, lines that are slanting, lines that are horizontal. So you'll see some parts of these models will pick up these patterns. The next part would essentially put together to make shapes, like a circle versus a oval versus a let's say a stop sign and things like that. All right. And then the third layer might essentially put together all these relative shapes. Oh, if you have two eyes, a nose, and a mouth, then it is a face. Then the last most layer can actually do, oh, this kind of a face is a human, this kind of face is a dog, with this kind of face is a cat, right? And then the other one final most layer can actually be able to identify a specific breed of a dog. Oh, this is an Alsatian, this is essentially a Pomeranian, this is essentially a this is a poodle, and things like that. So there is some level of analysis that you can do, but it is not that foolproof, which is exactly the point that I was trying to say in the end, where the explainability of exactly what are all the things that it used. Oh, first it figured this, then this, then this, then this, and that's why it is saying this is what it is not exactly that we can actually do today. We can understand at a high level, but not quite. Okay. So actually, one of the very first use cases where we will talk about dictionary encoding, we'll also talk about a concept, something called embedding. And in that, I'll give you some numerical examples about how we do that in language models, and you may be able to draw some parallels into the application in medicine as well.
Okay, thank you.
Right?
Yeah.
So I think we went really overboard a little bit. Any
Yeah.
other questions? Probably I'll stop the recording and then I can take some more questions.